Hello, everyone. How are you guys doing? Hi, Musfika, Apollo, Kimberly, Josie. How are you guys doing? Can you guys hear me well, or you're hearing double? For some reason, I'm hearing myself twice. You can hear me well? Okay. So, okay. So, you know, I can't believe we had only 4 days, 4 classes. I feel like class started long time ago. It's been a month. But now when I reflect, I noticed that we had only 4 days lectures. That's it. So today's our 5th day, and I think you guys are having a break, right? You are having a break in school. I'm not wrong. Mid-winter break. How lucky you guys are. In college, you have only one break. It will be end of April, if I'm not wrong. And it will be for 1 week. So we are going to have, we're going to miss 2 classes in April. Okay, so it's so nice to see you guys again. If you email me saying that you cannot make it because of the weird schedule, I understand, no problem. And also if you told me that you cannot make it tomorrow because you are having a break, so you are not even here in New York. So if all of you want, we can have tomorrow's class online. If only you want, so that people who are on vacation, they can join online. We'll talk about it later, okay? At the end of the class, if you're interested. Now, what we have here is still chapter 1. So we are done with almost all the sections except for one topic, continuity. Once we are done with continuity, then we are going to do derivative. So most likely we will be able to finish this today, and tomorrow we are going to start derivative. Okay? Any question, comments, concern, complaint, anything so far? If you don't want to write on the chat box, you can unmute yourself and talk on the microphone. No complaint from anyone? Okay, so continuity. Continuity is a fun section. It's a fun topic. In continuity, we are going to talk about limit. We are going to connect limit with continuity. So in general, what is continuous function? A continuous function is a nice function which doesn't have any hole or any jump. And if you want to describe continuous function to anyone in a short word, it will be a function is continuous if you can draw it without ever lifting your pen or pencil. Then it's a continuous function. We have a formal definition, but as long as you understand the informal definition, the formal definition we need to worry about in this class. Now, any point where we have a hole or a jump, the function is not continuous. And when the function is not continuous, we call them discontinuity. Now, in order to be continuous, we can connect limit with the continuity. So a function f is continuous at an x value a if the limit when x goes to a for that function is the same number as the y value of the function at that x value. Okay, so when the limit and the y value are the same number, then the function is continuous. So this definition tells us three things. One, that our y value must exist. So f of a has to be defined. Then the limit of the function must exist. So you see, we did many examples where the limit of the function did not exist because the left side limit wasn't equal to the right side limit. So in order to be continuous, our first condition, our y value must exist, our limit must exist. Now, in order to limit to exist, we have to have the left side limit and right side limit the same number. So the limit exists, it tells us that since the limit exists, that means there must be no jump in our there cannot be any jump in our function. My computer is saying something. It's almost time to restart. Up to date. Write it out. Write it out. Okay. Why it's keep saying you have to restart? You know what? I'm going to ignore that notice. So first condition, y value must exist. Second condition, limit must exist. And the third condition, the limit and the y value must be the same number. So if the limit and the y value are the same, that means we are not going to have any hole in our function. So when we have these three conditions fulfilled, that means our function is continuous at that x value. And then if you check every x value for this condition and every x value satisfies these three, that means the function is continuous everywhere. Now, this is an example where the function is not continuous. So in the first example, in the first number 1, x value 1, the function is not continuous. There are two reasons. One reason, the y value, there is a jump. There is a jump here. The left side limit is one number, but the right side limit is another number. So we have a jump. So the function is not continuous. In the second one, the function is not continuous. It's because even though the limit exists and the y value exists, but the limit and the y value are not same. They're two different things. So at when x is 2, at the place of the y value, we have a hole. So the function is not continuous. Same thing, our third point, we have a problem because we have a jump. The left side limit and the right side limit are not same. So the limit doesn't exist. As a result, we have a jump here. So this function is not continuous because we have a jump and hole. If you look at the next example, the first one, the left side limit is going toward this y value, let's say 3. The right side limit is going toward the same y value 3. So our limit does exist. Our limit when x goes to 2, the left limit and the right limit, both limits are same. So the limit at 2 is 3. So limit does exist. But look at the y value. When x is 2, there is no y value because we have a hole there. The y value doesn't exist. So since the limit and y value are not same, it's not a continuous function. The next one looks very similar to this one, we still have the same limit, let's say 3. So we do have a limit, and this time we do have a y value. When x is 2, our y is 1. So we do have a y value, we do have a limit. However, still this function is not continuous because the limit and the y value are two different numbers. So this function is not continuous. Now, if you look at this example, it also has the same problem. The both side limit, the left side limit is going toward infinity. Same thing, the right side limit is going toward infinity. So the limit does exist. Limit is infinity when x is 0. And when x is 0, we do have a y value. This is the y value they gave us. Y is 1. So limit exists, y value exists, but since they're not same, the function is not continuous. Now you try one. Think about what could be the reason for which multiple choice makes sense for this graph. A is saying the limit is 6. B is saying limit doesn't exist. C is saying limit is 4. C and D saying limit is 4. E is saying limit is 6, but it's not continuous. So A is saying limit is 6 and it is continuous. E is saying limit is 6, so it's not continuous. B is saying the limit doesn't exist and not continuous. C is saying limit is 4, but still it's not continuous. So what do you think? Which choice makes sense here? Which is correct? I guess they are B. Okay, B, C. Apollo, why did you pick B? It says limit doesn't exist. So in order for limit to exist, the left and right has to be same, right? So what is your left limit and what is your right limit when x goes to 2? Apollo, 4. See? So when x goes from the left side, our y is 4. When x goes to from the right side and left side, y is still 4. So limit does exist. So B cannot be correct. And most of you agree with C. Let's see. C says limit is 4. So this is correct. Our limit is 4. But still it's not continuous. True, it's not continuous because the y value and the limit are not same. The function is not continuous. Do you see your mistake, Apollo? Do you agree with us to the answer I see? No, don't be sorry. I'm so glad that you picked the wrong one because since you picked it, I could explain it to you. Okay? I actually love wrong answers because I can show you why the answers are wrong. Any question from anyone? No? Okay. So now I'm going to do one example. I'm going to walk through one example and I'm going to give you 3 examples to do. So in this example, they're saying, is this function continuous at 2? So we have a piecewise function. This is called a piecewise function because we have 2 different functions combined in one plane. Our first function is a parabola. The second function is a line. So they are saying for x equals 2 and smaller than 2, our function is a parabola. And when x is bigger than 2, our function is a line. Now we want to check whether this function is continuous at 2. So before 2, it's definitely continuous because it's a parabola. And as we know, parabola is continuous everywhere. And after 2, it's also continuous because it's a line. And we know a line is continuous everywhere. So before 2 is continuous, after 2 is continuous, So we only have problem at 2 because at 2 they are meeting. And we have to see whether they are continuous or not. So in order to prove that, we are going to work with the 3 conditions we just mentioned. The first condition says our y value must exist. And here y value does exist because when x is 2, we replace our function, we replace our x value into the first function. When x is 2, our graph is a parabola, and from the parabola, we get our y value is 5. So y value exists. Second condition says the limit must exist. So in order for the limit to be existed, the left and right limit has to be same. So left limit, when you walk from the left side, our function is a parabola. So you replace 2 into the parabola, and we got our limit is 5. When you walk from the right side, so this is 2. If you want to see visually what is happening, 2, 1, 0. Okay, somewhere like this. We have a parabola and then a line. And we want to see whether we have a hole here or closed circle. So when you walk from the right side, we are walking on the line. So for every number bigger than 2, our function is the line. So we place 2 into the line and we found the y value 5. So the left limit is 5, right limit is 5. That means our limit does exist and it's 5. So our second condition fulfilled. First condition says y value must exist. It's true. Second condition is limit must exist. We also found it's true. And now the last thing we need to observe is that whether the y value we found in 1 and the limit we found in step 2 are the same number or not. Well, they are same. When x is 2, y is 5, and we found the limit is also 5. Since the y value and the limit are same number when x is 2, that means the function is continuous because it fulfilled all 3 conditions. Okay? Any question? This you can see. Was any step unclear or confusing? No? Okay, then it's our prayer time, so I'm going to pray. So I'm giving you 3 examples to do. In the first one, you are going to check where this function is continuous. In the second example and third example, we are going to see for which value of c will make this function continuous. Okay. So let me give you a hint. Just like the example we walked through, in here, for every number smaller than 0, our function is a square. So we have 0 and 2. Before 0, it's a parabola, so it's continuous. Between 0 and 2, it's a constant function, a horizontal line. After 2, it's an increasing line. So it's continuous everywhere. We just don't know whether it's continuous at 0 and at 2. So we are going to test the exact same thing as we did on the left page. We are going to do it twice. Once for the 0 and once for the 2. For the second function, in order for them to be continuous, the number we get from here has to be the same number we get here. So this is your hint. The y value is supposed to get in the first function when x is 0, we have to have the same y value when our c is not 0. And similarly, the last one. In order for them to be continuous, then we want the 2 function must be equal when our x value is 3. So I give you the hint. I'll give you 10 minutes. I'm going to pray. I'll be back in 10 minutes. You guys can discuss with one another, okay? Actually, feel free to talk with one another. or with your friends. Okay, bye bye. See you in 10 minutes. I'm back, guys. I see so many conversation going on. Good, thank you. So, what do you think about the first one? Is F continuous everywhere? Okay, so you think it's continuous from negative infinity to 0, then 0 to 2, and then 2 to infinity. The difference between your answer and Carrie's answer is that she's including the 2. I understand. I can rule. Okay. Great. Yeah, Ellen, you have a tiny mistake. It should be bracket, not parentheses. Why? Because see, 2 has an equal sign, whereas 0 doesn't. So at 2, as long as the answers are same, the y value, then 2 is included. So let's see. The first one. When we have x is bigger than, sorry, smaller than, when, how do I make it bigger? No. View. Okay. Oh man. Ugh. Okay. What's wrong with this? It's moving on its own. Um, I don't need a third document. This one? Okay. And I lost everything. Yeah. It's happening after the update. Windows forcefully updated my computer from Windows 10 to Windows 11. And after that, my Microsoft Word is acting so weird. Okay, let's see what do we have. It's saying that, like I said, before 0, so we have 0 and 2, the problem. Before 0 is a parabola, between 0 and 2 it's a line, and after that it's an increasing line. So one thing you notice, the first thing you notice is that in here or in there, in both cases, 0 is not included. That means when x is 0, y value doesn't exist because our domain doesn't even have 0 in it. So we actually don't even have to check 0. At 0, it's automatically not continuous because 0 is not in the domain. So y doesn't exist. So definitely at 0 or y value doesn't exist as a function is not continuous because of the equal sign is missing. Then at 2, so we have to check what is happening at 2. When x is 2, we have to see, do we have an y value? When x is 2, 2 has an equal sign here. That means when x is 2, our function is the middle one. So our y value is a constant function 6. So I'm writing here, but it's writing there. What's wrong with this one? Man. Okay. I'm writing here, but for some reason it's showing there. Anyway. So y value does exist. And then we want to see when x is ESLM. 2 gets a bracket because it does exist at 2. So our y value exists, first condition satisfied. Not, let me take a new page here. It's driving me crazy. Let me insert a page. Okay. Let me get out of this page. So let me write again. Oh man. Okay, let me see what happens here. What's wrong with these? I'm writing in one place, but it's writing in the other place. Let me close it and reopen it. I'm so sorry, guys. Don't save, don't save. Save. Technology. Sometimes I wonder about our future. Like the way everything is depending on technology. What happens if technology breaks down? Then how our life will be. Okay, probably I can write here, hopefully. So let me get out of this page and right here. Okay, ignore this. Why can't I? Um, come on. What happened? Okay, what are you saying? Y value. So when x is 2, we do have a y value. It's 6. So it's telling us that 2 equals 6. So it satisfied the first condition. The second condition, Carrie, you're right. Okay, Sanjeev, how come you have school? Everybody has no school. They're on a break. How come you're not on a break? Um, the next one, we see. Oh, that's why. So next you have to see the limit. Limit x goes to 2 from the left side. So on the left side, before 2, we have y equals 6. So our function here is 6. So our y value does exist. The limit does exist. It's 6. And limit when x goes to 2 from the right side. 2 from the right side, our function is 2x. So it's 2x. So to get the limit, ah, 2x. So 2, which is 4. And 6 is not 4. So the limit at 2 of the. Did you guys get the same thing, or did I make a mistake here? Success Academy. Good, Sanzim. So you got the same. That means, Ellen, you are actually correct. We cannot put bracket for 2 because even though the y value does exist, but the function doesn't, the function is not continuous at 2. So the function is continuous from negative infinity to 0, and at 0 it's not continuous. Not continuous. So we put a parenthesis. And then from 0 to 2 it's continuous, but same thing at 0 it's not continuous, at 2 it's not continuous. So since at 2 is not continuous, so you have to put parentheses. And then it's continuous after 2 to infinity. So it should be parentheses 2. If we have an open interval and a closed interval at the same time, the closed one fills the open one. So what you see, the y value does exist at 2. When x is 2, our y is 6. But in the third interval, when x is 2, our y is 4. Y value does exist, but the function doesn't exist. The limit doesn't exist because the left limit is 6, but the right limit is 4. So it's not continuous. So if you want me to show you the correct version of the graph, before 0, we have parabola. So when x is 0, we have a 0. So we have a hole at 0. And before that, it's a parabola. Now between 0 and 2, it's 6. So we have a hole here, but we have a closed circle here. And after 2, the function is 2x. So when x is 2, our y value is 4. And then the graph is going on. So this is actually the graph. So see, is the graph continuous? Oh, at 2x, it's a hole. Do you see, Carrie? Look at the function, look at the graph. By looking at the graph, does it look continuous? No. Yeah, and it's asking where it's continuous. So we only can close circle when it's continuous. At 2, y value does exist, but it's not continuous. We cannot have a closed circle. Any question from anyone? No. Okay, and as you guys found, the answer is 1/4. Yep, the answer for this one is 1/4. So the hint here is it says where is the function continuous at 0? So in order to be continuous at 0, we have to have the same y value at 0 for the left function and for the right function. If we have the same y value, we're going to get the same limit because the second function is constant. So they're going to give us the same result. So in order to be continuous, a condition is x over x cubed plus 4x. It has to be same as c when x is 0. But we have a problem here. When you replace x with 0, we have 0 over 0, which doesn't exist. So we cannot substitute x with 0 here. So we have to modify the function. So in order to modify, we can pull out x from the denominator as a common factor. We get x squared plus 4. So top x, bottom x cancel out. We get simply 1 over x squared plus. And now we can substitute x with 0. Our x is 0, so we get 1 over 0 plus 4 equals c. That tells us our c is 1/4. So as long as our c is 1/4, then the function will be continuous at 0. Any question? No? Are you guys okay? Okay. The next one is same. Why this function is continuous? Or is this function continuous everywhere? So we have a problem at 3. Before 3, the function is a square parabola. After 3, the function is a cubic, so this shape. So parabola is continuous everywhere. Cubic function is continuous everywhere. So before 3, it's continuous. After 3, it's continuous. The only place we don't know whether it's continuous or not is at 3. Exactly. Polynomials are continuous everywhere. As long as your function doesn't have any problem, it's continuous everywhere. It doesn't have to be a polynomial. Like, for example, absolute value, it's not a polynomial. Basically, it's still continuous everywhere. It doesn't have any problem. Okay, so same concept. In order for them to be continuous, we have to have the same y value for both function when x is 3. So we set both of them, the first function and the second function, they must be same when x is 3. So you can substitute 3 here because it doesn't have any denominator. So you're not going to get 0 over 0, and you can simplify. So our x is 3. Every x you see. Why this ink is not okay. 3, 3, 3, 3. Every x is 3 in both sides. So we get c times 3 square, 8 times 3, 3 cube, c times 3. And we simplify. We have 3 square, 9c. 8 times 3, 24. 3 cube, 27. And so to solve for c, we want this 3c from right to the left. So we get 12c. The 24. So we get rid of the 24 from both sides. We have 12c gives us 3. That means c gives us 12 over 3, which is surprisingly same number as the last one, 1/4. Any question on anything so far we did? No question, no comments, no complaint, nothing? Okay, so anytime, guys, if you have any question, if you think anything is unclear, please let me know. I would love to help you with your problems. So here is my solution. Next, we're going to talk about few properties. Basically, they are saying if you add to continuous function, it will be continuous. If you multiply to continuous function, it will be continuous. If you subtract continuous function, it will be continuous. It will be continuous. If you multiply a continuous function with a constant, it will be continuous. So whatever you do with continuous function, the result will be continuous. And then the theorem says polynomial is continuous everywhere. A rational function is not continuous, what makes the denominator 0. Okay, so rational function is continuous only when its domain So rational means you have a numerator over a denominator. That 0 is continuous everywhere except what makes the denominator 0. The function means, so polynomial is continuous everywhere. Rational function is continuous only its domain. Root function is continuous only its domain. And similarly, trigonometric functions are continuous only on their domains. So remember, domains. Domain means where the function is defined. It means when we have a y value for the x value. Okay, now one example, interesting example. Suppose f and g are two continuous functions, and g of 8 is 4. And then they give you the limit of 3 times the f function plus the product of f and g. The whole result equals 35. Then what is f of 8? Think about it. F and g are continuous, and g of 8 is 4. We want to know what is f of 8. And they gave us one information. No, you don't have to use. Yes, you can use rules. You don't have to, because we have this theorem. This theorem is telling us whatever you do with continuous function, the result will be continuous. And they're telling us the two functions you're working with, they're continuous. So we don't have to prove continuity. They're only telling us that whatever results you're going to have, they're continuous. Yes, you're going to use a hint. Let me give you a hint. You are going to use the rule is that limit x goes to a of f of x is f of a. This is the rule you're going to use, which we learned a few minutes ago. The function will be continuous at a if the limit is same as the y value at a. So you guys try it. Let me take the attendance. You're already done, Ellen? And Apollo and Sanzim? Oh man, you guys are too smart. Yep, the answer is correct. Let me take the attendance. If you're already done, because it's 7 times 35, 735. True. Let me see, what do I have next? So if you're not done, you can keep doing your work. And if you're done, you can write down this information about domain. The next thing you're going to do is learn about domain. Okay. Today is 2:18. I'm taking attendance, okay? Kimberly?
Here.
Great. Carrie? You're still there, right, Carrie?
Yeah, I'm here.
Judith? Here? Judith, did you say here?
Yeah, here.
Okay. Mac?
Here.
Perfect. Ziad?
Here.
Chi?
Here.
Jocelyn?
Here.
Anjum Trot. Lucas?
Here.
Hoi Lam. Here. Logan? Logan. Vacation. Ellen is here. Muspika? Are you still there?
Yes, here.
Perfect. Nicholas, not here. Sanzim here. Shion,
Here.
okay. Raka, are you still there?
I'm here.
Okay. Ella,
Here.
great. And Apollo, are you still there?
Yeah.
Perfect. And lastly, Andy. Yeah, okay. Great. I have everyone except two. Um, okay. So let me go back to the question real quick. Why are the domain for even and odd different? I will show you. Before that, let me go over this question real quick. So as you guys figure out, it's actually not a tricky question. It's very simple. First, we start with the limit. The limit rule says we can distribute the limit. So limit goes to the first one, limit goes to the second one. So limit 3 f of x plus limit x goes to 8 f of x, and also limit is distributable in the multiplication. So we get limit x goes to 8 of the g of x. Now constant we can pull out in the front. So we get 3 limit x goes to 8 f of x. But they're only telling us that f of x and g of x are continuous function. What does that mean? It means the limit of this function at x value a is same as the y value at a. So in our case, our limit is happening at 8, and now it's happening again. So this is same as, I don't know what to do. 3, I hate this. What's wrong with this? It's 3. Okay, let me take a page on the other side. Okay, so 3 f of 8 plus we have f of 8 times g of 8. So we have f of 8 we are looking for, so we pull it out as a common factor. We get f of 8, 3 plus g of 8 equals 35. So f of 8 is 35 over 3 plus 4 because g of 8 is 4. So it's 35 over 7. That gives us one size 5. Let me close it and reopen it again. Man. What's wrong with this thing? Oh, not that. See, I opened one thing, but they opened another thing. Okay, so let me talk about why domains are even and odd are different. Okay, so root means we are finding same number when you multiply radical many times, that gives us the insight. For example, square root of 4. So which number, when you multiply square times, means twice, the result is 4. And cube root of, let's say, 8. It means which number you are multiplying cube times, means 3 times, so the result is 8. Okay? So this is what radical means. Which number, if you multiply radical many times, the result is whatever number you have inside the radical. Now, for even root, like square root, fourth root, sixth root, eighth root, for even root, we have a problem with the negative number. We don't know what is square root of -4. We know square root of +4 is 2 because 2 times 2 gives us 4. But what is square root of -4? We don't know because if you think it's -2, -2 times -2 is +4. But you're looking for square root of -4, not +4. So square root of any type of negative number doesn't exist. And that means we have a problem. Only our domain for the even root function exists only when our inside whatever function we have inside the radical is positive. The domain for that function is only can be 0 or positive. On the other hand, if you look at square root of -8, so the cube root of -8, it does exist. Cube root of -8 is -2 because -2 times -2 times -2 will give us -8. So anytime if you multiply add many times, it becomes the same number with the same sign. So if you multiply a positive number 3 times, the answer will be positive. If you multiply -3 times, the answer will be negative. So add root does exist for every number, positive, negative, or 0. It doesn't have any problem. So domain for add root is all numbers because it doesn't have any problem. On the other hand, domain for even root, okay, this is not what I'm looking for. But the domain for even root is restricted only to positive outcome. Do you understand now, Sanzim? Okay. Let me show you some visualization. Desmos. Look at square root. I have to small letter. Square root of 3x minus 5. See? The graph only starting from here. It doesn't have anything before that. But look at cube root. 3x minus 5. Cube root means 1/3 power. Look at the cube root function. See? It exists everywhere, the blue one. The same function, if it's under the square root, its domain is restricted. But if it's under cube root, its domain is everywhere. So add root doesn't have any problem, but even root, they do. Okay. That's why, depending on the function, whatever function we have different types of radical, different types of domains. So polynomial and add root, they are the nicest functions. They have no problem. Their domains are everything. Problem starts when you have a add root, like just like the example I showed you. In order to figure out what's the domain of an add root, even root, we take the function inside the even root and we set it bigger than or equal 0. Here, for example, let's say what is the x plus 5? What is the domain of square root of x plus 5? So in order to find out the domain, we take the function inside x plus 5, and we know that inside must be positive, which is bigger than 0, or it can be equal 0. So we set it equals bigger than 0 or equals 0, and then you solve for x. So you subtract 5 from both sides. So domain for this function, starting from -5, everything bigger than 5. From -5 to everything bigger than 5. And you're allowed to use -5 because square root of 0 is 0. So that's how we find the domain for every even root. Now for rational, we have only one problem. Rational function cannot have a 0 in the denominator because we don't know how to divide by a 0. Divide by a 0 means you are going to divide something into 0 pieces. 0 pieces means you're making it disappear. Well, we cannot make anything disappear in our real life. Magicians, they do disappear things, but they cheated in their disappearing method. So that doesn't count. In our real life, we don't know how to disappear anything. So our denominator cannot be 0. So if you have a function, let's say 1 over x plus 5. For rational function, or let's say x plus 3 over x plus 5. Whatever we have on the numerator, as long as it's a polynomial, we don't care. We only take the denominator. And we say, well, whatever denominator we have, that cannot be a 0. So we see what makes the denominator 0. We solve for x, so we subtract 5 from both sides, and we find that, well, we can have any number for our x, but we definitely cannot have -5 for x. So our domain is from everything from -infinity to -5 and -5 to infinity, except for -5 because that makes the denominator 0. Then we have a combination. What if we have the even root function on the denominator? For example, x over square root of x plus 5. Now again, as long as our top doesn't have any problem, ignore. And only concentrate on what has a problem. Denominator has a problem. And now we have two problems. One is our denominator. The entire denominator cannot be 0. So it definitely cannot be 0. And the second problem is whatever we have inside here, that thing also has to be positive. Means it has to be bigger than 0. So if it was single, we say it can be 0 or bigger than 0. But now you're saying, well, since this is on the denominator, so now it cannot be 0. That means the only thing it can be is bigger than 0. So we take the function inside the radical and we set it bigger than 0. This time we cannot include our equal sign here because we don't want the denominator to be 0. So our domain is everything after -5. We cannot take -5. So -5 to infinity with the parentheses. And now the last type of problem. What if we have a radical, let's say this radical on the top, and we have a rational on the bottom. Let's say x plus 3. Now both numerator and denominator, they have problem. So we have to find the domain individually and see where do they intersect. So this domain is starting from 5. So it's starting from -5 and everything bigger than -5. And this domain is telling us, hey, you can take everything else, just don't take -3 because -3 will make the denominator 0. So if you visualize this, the top one is saying start from -5, but don't take -3. And then you're allowed to take everything else. So start from -5, don't take -3, and then take everything else. So this is our domain. We can take anything from -5 to -3, and then -3 to infinity. So -5 to -3. We're allowed to use -5, no problem with that. But we definitely cannot use -3. That makes the denominator 0. And then after -3, we don't care about anything else. We are allowed to have everything in our, we can have everything for our x. Actually, I shouldn't say where they intersect. I should have said where they combine. Okay. Any question on any of the function? So there are 6 types of problem, and we have 6 ways of finding their domain. No question from anyone? Okay, then let's do some example. We are finding domain for these 2 functions. What do you think the domain for the first one? Which category the first function fall under? Yep, all real numbers. So domain doesn't have any problem because this function is actually a polynomial, and polynomial doesn't have anything. And you think the first one has to be bigger than 1? What if 0? When x is 0, do you have any problem, Ellen, for the second one? Why it has to be bigger than 1? What is your reasoning? What's the domain for the first one? Square root of x. 0 to infinity. And can we include 0, or 0 we cannot include? Is it bracket or parenthesis? Bracket. Because we do know what is square root of 0. Square root of 0 is 0. It does exist. So we can have 0 here. Now what's wrong with the second one? Exactly, between 0 and 1. So what's wrong with the second one? Can we have everything in our second function? We cannot have 1. So there's only one number that is a problem. So that means from -infinity to 1, and then from 1 to infinity. So let me actually plot them. The first function says start from 0, go to infinity. So this is 1. The second function says take -infinity to 1. So 1 is here. So second function says, hey, don't take 1, but take everything before 1 and after 1. And now the third one. Do we have any problem with the third one? Is there any number that makes the third one denominator 0? No. It's always positive. So -infinity to positive infinity. So the third one says, hey, take everything. I have no problem. Now, where do you see the 3 of them make sense? We cannot use this part for the first one, so I had to get rid of them. And others are fine as long as we don't take 1. So domain for this function starts from 0, go to 1, but we cannot take one. So we break our function into two pieces, our domain into two pieces, 0 to 1 and 1 to infinity. Cool, right? We have three different functions and we combine their domain and see what's the result at the end. Is there anybody who did not understand what we are doing? Anyone? If you don't understand, please don't feel shy. Just ask me. Even if you think it's the stupidest question, no problem. I love stupid questions. So does anybody have any silly question you think? Any normal question? Any weird question? Any question at all? No? Okay. Now we are going to go composite function. Composite function, basically they are saying that if you have one function sitting inside another function, we can actually insert the limit into the inner function. So you can move around your limit. And as long as the function is continuous, whatever limit we get from the function, our y value will be the same thing. So that's the main idea, okay? One example here. Use the continuity to evaluate the limit. What's the limit of this function? They didn't tell us whether this function is continuous or not, but they're telling us use the continuity. So we all know sine function is continuous. This is sine. Sine is continuous everywhere. It doesn't have any problem. So even though they did not tell us, but you do know sine is continuous, so you're dealing with continuous function. How do you think we should approach this question? Any idea from anyone? Yeah, we're going to substitution because it's a continuous function, so we can move around the limit. So we simply can do substitution. And why we can do substitution? Because it's continuous. So the way they want us to do this question is this. Move your limit inside the sign. So 3 sine limit x goes to pi of x plus limit x goes to pi of sine x. This is what they want us to do. But in other words, they're basically telling us, hey, substitute them. So we get 3 sine, one is substitute x with pi, we get pi here. One is substitute x with pi, we get sine pi. And Panda says do parentheses first. Means first simplify this. So we need to know what is sine pi. Do you know what is sine pi? Good. Sine starts from 0, goes up, goes down, and then ends at 0. The highest it can have is 1, the lowest it can have is -1. And to complete one cycle, it goes to 2 pi period. So exactly in the middle, we have 1 pi. So sine pi is 0. And we know 0 plus anything is the anything itself. So sine pi. And we know again sine pi is 0. So 3 times 0 gives us 0. Okay. So it is actually a fun question, right? Any question on this one? Any comments? Anything? Nothing? This is actually from your homework. Okay, don't forget to do your homework, guys. Chapter 1 homework, I don't remember when the due date. But you actually have all the knowledge now to complete all the homework from chapter 1. So please do all the homework for chapter 1. Whatever you don't know, you can ask me tomorrow. Okay, the next one, a fun theorem, intermediate value theorem. It's a fun theorem plus a very important theorem. An important property of continuous function is expressed by this theorem. What is this theorem? It's saying that suppose you have a continuous function and that function is continuous on a closed interval. And let n be any number between the two y values we have. So our closed interval, the x values are running from a to b, and between them, for a we have a y value f of a, and for b we have a y value f of b. And it's a closed circle. It means the y value does exist. So y value does exist for every point from a to b. They are saying that suppose you have a number n that is lying between f of a and f of b. So this is your f of a, this is your f of b. If you have any number n that is lying between the two y values, then for that n, you must have to have an x value that is lying between the two x value a and b. So the condition they're putting here is that the two y values you have, they cannot be the same y value. Because if you have the same y value, this condition may not satisfy. This condition will fail. For example, a line. Let's say this is 0 and this is 5. And let's say this is y value 3. So if f of a and f of b are the same number, then we cannot use this theorem. Because it doesn't make sense. So in order to apply this condition, we cannot have the two y values same at the end. Whatever you have for a, the y value, and whatever you have y value for b, they have to be different from one another. If they are different from one another, then for any number between the two y values, we must have an x value that is lying between the two x values in the interval. Okay. Now, we have an interesting question. Show that between x value 1 and x value 2, there is a solution of the graph. What does solution mean? Where do we find solution of any function? Zeros. Good. i.e. when x is 0. So they're telling us we have between 1 and 2, we have a function. It's a cubic function. How do you draw cubic function? Something like this. Okay. So we have a cubic function. And the two y values we have, let's say one y value is here, let's say another y value is there. Two y values we have, then there exists some y value between these two or somewhere, so that for that y value, we have x value here when our x is 0. Sorry, x is not 0, y is 0. So x is 1, x is 2, y is 0. My bad. When our y is 0. Any idea? How can we apply the intermediate value theorem to show that between the two y values, there exists one y value which is 0? Change in sign. Good job, ND. So, in order to have a y value 0, we must have to cross through the x-axis. So when you cross through the x-axis, our y value is changing. One of them is positive, one of them is negative. So in order to have a y value 0, our two y values must be different. Two different signs they must have. So let's see what is happening when x is 1. When x is 1, our y is 4 times 1 cube. 6 times 1 square plus 3 times 1 minus 2. So what do we have? 4 minus 6 plus 3 minus 2. 4 and 6, 4 and 3 gives us 7. 7 minus 8 is negative 1. So when x is 1, let me fix my graph now. When x is 1, our y value is negative 1 here. And when our x is 2, what is happening to our y value? 4 times 2 squared, 6 times, 4 times 2 cubed, 6 times 2 squared, 3 times 2 minus 8. If you're already done with this, can you give me the answer here? I'm too lazy to write them down. All the details. How much we have for the y value when x is 2? Yeah, minus 2. Wait, minus 2? No, minus 1. This is 3, right? 4 plus 3 is 7. 7 minus 8 is minus 1. Oh, thank you. It's 2. Yeah, I see now. Thank you. You guys are very good. And I'm really happy to teach you guys. I'm very excited. So what is our y value when x is 2? 12. It's way up here somewhere. Perfect. So see, if you have a one y value negative, another y value positive, so in order to, since this is a continuous function, so in order to go from one y value to another y value, you must have to cross the x-axis somewhere. So intermediate value theorem says if the two y values are not same for the two x values, then if you're dealing with a continuous function, there exists some y value between the two. So this is f of a, this is f of b. So if and this is 0. So if you have a number between f of a and f of b, then there must exist an x value c. We don't know how much is that. What's the value? There must exist an x value between a and b so that f of c will give you that y value. So we don't know which number is c, but intermediate value theorem guarantees that there exists at least one solution between x value 1 and x value 2? Any question? Could you factor to find the solution? Yes, but the thing is they're not asking for solution. They're asking show that we have a y value 0 between 1 and 2. No problem. That's why actually we love this intermediate value theorem, because it doesn't matter what complicated question they give us, as long as we have two different y values, it's a guarantee that we are crossing x-axis. So we have a solution there. Okay, then the next question, the next topic. Carrie, question?
Yeah, the question that, like, can you go back a slide?
Mhm.
On a test, like, how would we say that there is a solution? Like, do we just show the same work and then just, like, is that it?
That's it. You
Okay.
find f of a, f of
Yeah.
b, and when you see the sign is changing, so you say by intermediate value theorem, it's a guarantee that we have a y value 0 there. And when y value is 0, that means we have a solution.
But we have to write, like, explaining, like, as per the intermediate value theorem, sign change, blah, blah, blah. Like, do we have to say all that?
You should at least mention the intermediate value theorem.
Okay.
Like here it says f is continuous. So by intermediate value theorem, it's a continuous function. I mean, by intermediate value theorem, we have a solution between x value 1 and 2. The main idea here is mention intermediate value theorem. And yeah, I'm planning to give one question on intermediate value theorem in the exam. Oh, and if you forgot, your exam is actually coming up. It's next Wednesday, if I'm not wrong. 1 week from tomorrow. The next one, continue. Why are this function is not continuous? So function is not continuous in 3 places. 1, when we have a hole. 2, when you have a jump or break in the function. And 3, when you have a vertical asymptote. So depending on whether we can remove or we cannot remove our discontinuity, we have 2 types of discontinuity. If anyhow you can remove your discontinuity and you can make the function continuous, then we call them removable discontinuity. For example, here, let's say this function is some type of function, and we know it's definitely not continuous when we have a hole. We can actually remove this hole. How? We can make this function into a piecewise function. And we say, well, f of x is this when x is, let's say this is 5. We can say f of x is this function when x is not 5. And when x is equals 5, let's say this is the y value 3, suppose. When our x is 5, our y value is 3. If we said that, that means we are saying, well, we can fill this gap by making our function into a piecewise function. And then you have a continuous function. So when you have a hole, we can actually remove this hole by making our function into a piecewise function. So that's why holes are removable discontinuity. On the other hand, when you have a jump or particle asymptote, there is no way we can fill that gap. When you have a jump, something like this, there is no way we can put something inside here and make it continuous. It's not possible. Similarly, when you have a vertical asymptote, something like this, or something like that. See here, our function is discontinuous and there is no way we can make it continuous. So that's why when you have a jump or vertical asymptote, we call them non-removable discontinuity. They have to stay discontinuous. Now, when do we get removable discontinuity? We get removable discontinuity by kicking or canceling a factor. So let's say you have a function, a rational function, and it's factorable. So in order to find the removable discontinuity, you must factor the numerator and denominator if possible. Once you factor, if you have something in common, you cancel them. And since you cancel them, they get angry and they said, well, you kicked us out, you canceled it out, so I'm going to leave a hole in your function. I will not make your function, I will not let your function to be continuous. So we factor, we cancel, and we set the cancel time equals 0, and they will tell us where our function will have a hole. For example, here, our function is a hole. How do you know? Because whatever function we have here, we kicked out a factor, and that factor was x minus 2. How do I know? Because when you set x minus 2 equals 0, that gives us x is 2. And see, we have a hole at x equals 2. So, main idea, how do we find removable discontinuity? We factor both top and bottom, we cancel, and whatever time we cancel, we set it equals to 0, we get the x value. Now, in order to find the y value of that hole, we replace the x value of the hole into the simplified function. And then we get the y value. So we can know the exact position of the hole in our graph. Now, infinity discontinuity, we get it at the vertical asymptote. And like I said before, to get the vertical asymptote, we factor both top and bottom. We cancel whatever is cancelable. And then whatever remains, the remaining denominator, we set it equals to 0. And that tells us where we have a vertical asymptote. So the difference between removable discontinuity and vertical asymptote is that removable discontinuity, we get it from the cancelled term by setting it equals to 0, solve for x. But vertical asymptote, we set the simplified denominator equals to 0 and we solve for x. Vertical asymptote doesn't need any y value because it doesn't have any y value. It keeps going on forever and ever and ever. So it doesn't have any y value. But a hole is a point. And every point has an x value and a y value. So we need to know the exact position of the hole. So we need the x and y. Okay. So this is a chart where I put together all the information, how to find each one of them. And if you observe, to find everything else, you're going to simplify the function first, except for the domain. Only for domain, we need the original denominator. You cannot use the simplified denominator to find the domain. So that's why I highlighted the domain. Only domain need original denominator. We set the original denominator not equals 0, or based on whatever function we have. If you have a square root function, then we set it bigger than 0. If you have a normal polynomial, we set it not equals 0, and we solve for x. That gives us the domain. But if and for everything else, for a rational function, to find the x-intercept, after you simplify, you set the numerator equals 0, you get your x-intercept. To find the y-intercept, you can use either one of them, either original one or simplified one, it doesn't matter. So to get the y-intercept, you set all the x to be 0 and you simplify the expression. The vertical asymptote is after simplifying whatever you have on the denominator, set it equals 0, solve for x. Removable discontinuity or removable singularity is after you factor whatever you cancel out, We said that cancel time equals to 0. We solve for x. Replace this x into the simplified function. We get the y. For horizontal asymptote, again, you can use simplified or the original one, doesn't matter, you get the same answer. But all you have to do is compare the result on the top and on the bottom and see their highest degree. If we have a highest degree on the top, we have no horizontal asymptote. If we have the highest degree on the bottom, our asymptote is always y equals 0. And if they have the same degree on the top and bottom, our asymptote is y equals their coefficients. So this is the summary of all the things. Any question from anyone? Yeah, Apollo, I posted the review sheet on Brightspace. Well, I actually didn't see you guys chat. Let me see what you're talking about. Okay. So now combining all this information before we leave, let's do one example. For this example, let's find out everything. The first thing you're going to do is find the domain. And for domain, we don't do anything. We simply take the denominator, and we set it not equal 0. We want to see what makes the denominator equal 0 so that we can omit them from the number line. So x squared minus x to the 4 cannot be 0. And now solve for x. So how are you going to solve for x? Any idea? Come on, guys, you have only 8 more minutes. Cooperate only for 8 more minutes. Factor, good job. We can factor out x squared. So we get 1 minus x squared. That means each factor, we don't want none of them to be 0. Yep, great job, Ellen. So we definitely cannot take x equals 0. And here we have 1 plus x, 1 minus x. So x cannot be positive 1 and x cannot be negative 1. So from the number line, we cannot take negative 1, 0, and positive 1. These 3 numbers. And we can take everything else. So domain in interval notation is from negative infinity to negative 1. We cannot take negative 1, so parentheses. So the first interval, second, is from negative 1 to 0. Again, we cannot take any at the end. The third interval runs from 0 to positive 1. And lastly, take everything else after 1. So 1 to infinity. So this is the domain. And now we are going to simplify and find the rest. So to simplify, we have f of x 2x plus x to the 4, and we already did the denominator factoring. How can we simplify? What can we do? We can factor, right, from the top. If we factor out x, we get 2 plus x cubed, and the denominator x squared, 1 minus x squared. Can you cancel anything here? X's. So you left it 1x on the bottom. And we got x times 1 minus x squared. And on the bottom, we have 2 plus x cubed. Since we canceled this one, since we canceled x, so that will give us removable discontinuity. Discontinuity. We set the cancel term equals 0 and we solve for x. Well, x is already solved. Oh man. But we cannot find the y. When x is 0, denominator becomes 0. Numerator is a whole number. So we actually have a vertical asymptote. So we actually don't have a removable discontinuity here. No removable discontinuity. Because we thought it's a removable discontinuity, but we just learned that it's not removable. It's a vertical asymptote. A number over 0 means vertical asymptote. So we can do vertical asymptote next. Vertical asymptote is simplified denominator equals 0, and then you solve for x. So simplified denominator is x, 1 minus x squared. We set it equals 0, and you already know that gives us x equals 0, and from here x equals -1 and +1. That's why we omitted them from the domain, because we have 3 vertical asymptotes. Let's find horizontal asymptotes. So for the horizontal asymptote, we compare the degree on the top and degree on the bottom. Y equals, what is the highest degree on the top? Okay, let me see. X-intercept. I already found x-intercept. Wow, you're great. You already found everything. Good job, Ellen. So our equation has x cubed, the highest degree on the top. And if you observe, here we have negative x cubed on the bottom. So we have the same degree. So that tells us our horizontal asymptote is y equals -1. So we found horizontal asymptote, vertical asymptote. Now let's find x-intercept. X-intercept is simplified numerator. So let me write top. Simplified top equals 0, and then you solve for x. So simplified top is 2 plus x cubed. We set it equals 0. Then we subtract 2. So x cubed is -2. And then we have to take cube root of both sides. So x is cube root of -2. Whatever that is, we don't know. I mean, without calculator, we don't know. Then lastly, our y-intercept, we set simplified, or it doesn't matter, original one, simplified x equals 0, and we solve for y. So we have y equals 2 plus x cubed, and then x 1 minus x squared. When x is 0, denominator becomes 0, numerator becomes 2. So y equals 2 over 0, it means it doesn't exist. What type of graph we are dealing with? Y-intercept doesn't exist, whole doesn't exist. And we have x-intercept, cube root. Horizontal asymptote is -1. Vertical asymptote is 3 places. So let me draw it's irrational. But let me draw the graph and see. It sounds so weird. We don't have any y-intercepts. How it's possible? So let me draw the graph. It sounds so weird. 2x, x to the 4. Let me make this. Let me make this smaller. Okay. So we have a rational. The top is 2x plus x to the 4. I have to write y equals. And the bottom is x square, x square minus x to the 4. Wow. Such a weird graph. See, this is the picture. We have a vertical asymptote at x equals 0. Let me see if I can draw here. I think it's not working again. So we have a vertical asymptote 0 is -1. That's why we don't have any x-intercept. Okay. Yeah, that's all we have. And with this, actually, we are done. The 1.3456. Tomorrow, we are going to start decided to do section 2.3. So tomorrow I'm going to skip 2.1, 2.2. And I want to give you all the derivative rules so that over the weekend you can work with the derivative problems. So I'm going to give you all the derivative rules and then we are going to do some example. Okay, tomorrow. So what do you think? Do you want to have an online class or in-person class? I have no choice. I have no problem. I can do both. So any comments from anyone? What do you want, guys? Online or in person? Okay, so 2 online, 2 like me, no problem. Okay, 3 online, 4 online. Okay, and then 4, no choice. Okay, then, since, okay, Carrie. Okay, so since all of you agreed, whether online or doesn't matter, so I'll make it online because only because you guys are having having a break. So it would be nice to do whatever you want to do, which is closer to your home or someplace. So yeah, we are going to have online. We're going to use the same link, same information, and I'm going to send out an email about that to whoever left already. Okay. So thank you so much. Before you go, if you want to take a picture of all the derivative rules, then it will be less work for you tomorrow. So just take a picture of the derivative rules. Where do I have it here? Okay. Let me delete all the annotation. So we are going to do this fast tomorrow. Write down all the rules. Oops. All the time. And then there are three things: equation of the tangent line, horizontal tangent line, and then what is velocity and acceleration. Yeah. So these are the information we are going to use in tomorrow's class. And tomorrow's class will be fun because derivative is the most fun in calculus. So I'm going to work with these rules, and I'm going to skip the original definition. Definition is I hate definition. Definition is kind of bad, but these rules are fun, very much fun. So thank you so much everyone for being here. Integral is more fun. Well, integral is fun, but the problem is derivative they have a solid outcome. But for integral, they don't have a solid outcome. We have to find the integral. That's why integral is less fun. But yeah, definitely after derivative, integral is the next fun thing. So we're on the derivative. Tomorrow we're going to the derivative. And I'm planning to go over all the questions from the review sheet. If you didn't see the review sheet, it's on Brightspace under the review sheet column. So I'm going to do all these rules, and then I'm going to do many, many examples based on all these rules. Okay? So dream about derivative tonight. Tomorrow we are going to have fun. Goodbye, everyone. See you all tomorrow online. Enjoy your night.
Have a nice day.
You too.
Have a nice
Bye bye. No problem. You guys also have a good night.